Yeah, drop, hey, huh.
Yo, what's up guys, this is 𝗪𝗚𝗟𝗟𝗟 and today I'm gonna showcase, as someone asked, the difference between heap and the stack, and I'm gonna go into some details about how the heap works, and I have made also a custom C program to demonstrate it. But first of all, let's begin and see how the memory layout is. So imagine it like this. We have the higher addresses up here and the lower addresses down there. The stack is actually on the higher addresses like this, and it stores local variables, function frames and stuff like that. And the stack, imagine that this whole thing is the memory layout. The stack grows downwards, so actually towards the lower addresses. On the other hand, we have heap, which is used for dynamically allocated memory, that grows on the opposite side. It grows upwards and towards the higher addresses. And what else do we have in memory? We also have the BSS segment, which stores global and static vars that are uninitialized or zero. We're gonna have a problem with that, I will explain it later. After that, we have the data segment, which has same stuff here, but it's about data that is already initialized with something. And after that, we have the text segment or code segment. You can see it both ways. And it's about the compiled machine instructions, for example, the address of main and stuff like that, registers. We'll see it inside the program. Some pros and cons about stack and heap. So about allocation speed, we see that stack is very fast in the way it allocates stuff. The heap is a bit slower. So about lifetime management, this is more like that, for example, in heap you have to say, okay, right now I want you to allocate this, for example, size of memory. After that I might free something. Okay, now I want to allocate more, less, and stuff like that, which is pretty much the same with the size limit. And in stack, we have a buffer, for example, that stores 20 bytes of data. That's it. And the program knows when, for example, something is filled, the rest is null and stuff like that, which also relies on the programmer. And we know that the data lifetime means the data that we store inside the allocated memory, even if it is heap or stack. For the stack, it remains until the function returns. After that, the stack frame is gone. And for the heap, it stays there until we manually free it, or with user input, whatever. Fragmentation, we don't have fragmentation in stack, but we have on heap. And safety, yeah, stack can be safer, but if the programmer is bad, for example, you don't take input limitations and stuff like that, it can also be risky. And heap is riskier because let's say that the way to find the bugs is a bit trickier, it needs more knowledge. It is not like, okay, I see I have a buffer of 20, I can read up to 100, buffer overflow. You play with other things like use after free, double free and stuff like that, that you need to have more knowledge about how the allocators work, which libc version you have and stuff like that. But I think that's enough of theory right now. Let's head into our program. So right here we see we have a program like this. It's a simple program. We have two global variables like this, the uninitialized and the initialized one. We have a wait function that has also two variables. And inside main, what we see, we have a fixed size buffer, and we fill it with wait hands. And after that, we create a dynamic object with malloc. We see that we request 0x40 for malloc to allocate for our first object, our first car pointer. For the second one, it's pretty much the same, malloc 0x40. And at the first one, we write first allocation, second one, second allocation. And after that, what we do, we free the first car pointer object we have right here, and we null it. This is a good practice because with things like that, you can avoid some double free, use after free and stuff like that. This is more advanced topic, I won't go into details here, but it's a good practice to null the pointer after you free it. Then we create another object with 0x60. As we can see here, we have 40 and then I request 60. I'll tell you why. And that's our third allocation after free. And the fourth one, 0x40 again, same size as the previous ones. Right here, we see that I print where everything should be allocated, like this. Then I call the wait function, which will print the addresses of these two variables. And last but not least, I free the rest of the pointers and I null them, and the program returns. So right now I'm gonna disable ASLR. And what is ASLR? ASLR actually randomizes addresses, and what I mean with that, right here, if I run LDD in my Heap program, we see that the libc, this is always the same. And why is that? That's because I have disabled my ASLR for the program. If I re-enable it, LDD Heap, we see that every time the program runs, this is randomized. This is not the same as this one. So this is actually ASLR. And what was it again? Echo. I'm gonna do 0. Okay, so right now we don't have ASLR again. And okay, let's compile the program. I use these flags, no stack protector, to disable canary. I want everything to be as simple as possible for the demo. No pi, no randomization, no need for that. And -g, this will actually enable debugging symbols. So okay, we run it, and what we see that our global var that is uninitialized is at BSS segment, and it is this address. The initialized one is at .data segment, which is this one. And if you actually pay some attention, you will see that, okay, this one and this one are pretty much the same. They are really close. And yes, that's the problem, because as I wrote here, this one will go to data instead of BSS. And that's why, because the loader maps them together into one region, because they have the same permissions. They both have read-write permissions. So yeah, that's it. And the rest we see wet, it's inside this text code. The heap variable we have is at this address, and the rest are stack. Okay, you'll say, okay, how you know that this is BSS, this is data, code, stack, heap, etc. We'll go inside the debugger and we'll see it right here. So we are inside the debugger, and let's say b main. Okay, let's run the program. Okay, before going step by step, let's first of all, for example, print this address. We're gonna do vmap and this one. And we see that it's the magenta, I don't know what color is this, which is inside the data segment right here. Don't be mistaken, heap is just the directory and the file name. This is not the heap, this is the data segment right here. So as we didn't expect, instead of going to BSS, this actually went to the data. And let's also check this, vmap, and this is also inside the data segment at this offset. We say it's pretty much close to each other. And what else do we have? We have the static stack here. And let's see, where does this lie? And we see that this is inside the stack right here. So let's proceed. Next instruction. I hope this is visible. So we are right here. This is gonna be our first malloc. Here is the first malloc. And then it's gonna be our second malloc like this. Let's continue. So we are at this point, right before the first free. We have done our mallocs, we have done our string copies, and again, we see that this is on the stack. This is not because there is no allocated memory yet. I will show you why. If we do this will show us the heap right here. We have some metadata here. What we see, we have 0x51, 0x51. If you remember, we did an allocation of 0x40, like this, 64. So the program knows, okay, in order to store this data with malloc, I will allocate 0x50 bytes of memory. And the one right here is actually the previous in use flag. This changes between 0 and 1. And what does it tell it? That the previous chunk is already in use right here. So that is why we have 1 right here and not 0. And we see our string first allocation, second allocation, that's right. And if I do again vmmap first, and if I print the address of first, we see it's this, and if I do xgx this, we see that it has this address, okay, and this address is actually, okay, so GDB kinda crashed, let's restart it. So we are right here again, and if we do vmmap, we see this, and what was the address again? We saw first, it has this, which is inside stack, but if we examine this address, like this, we see it contains this, and where does this lie? Vmmap this, and we see that this is inside heap. So that was the problem before. It's actually something pointing to something else, and the actual address of first lies in here. And let's continue. Right now we're gonna do our first free. We free it, boom, and let's also null it, and we do this again. And what we see here, our first allocation is gone, and we see tcache beans 0x50, 0 out of 1. I won't go into much details about tcache beans. Let's say it's some sort of fast allocations. So if we actually allocate a chunk that is this size, it will not create another one after our second allocation. It will just reuse this. So this is in short terms what it does. Then we do another malloc here. Yeah, our first allocation. As we can see, the third allocation, because it was 0x60 bytes, has this size, previous in use, blah, blah, blah. And we see that it's right after our second allocation. We proceed, we make the fourth allocation, which was 0x40 bytes, same as the previous one. And what we see instead, let me continue a bit. And what we see, instead of creating another chunk after our third allocation, it reused this one. And why is that? That is because it had same size as previously owned chunk, the previous one that was here. And what else we have here? Printf, okay, print. And let's continue until we hit the freeze. I hit the first free, second free, and the third one. And we see this. Okay, it has some junk right here, but it does not contain our strings of allocations and stuff. Yeah, also the method that will be printed is stored inside the heap. Let's continue, null, and this is actually it. And the program, after that, it will exit successfully. That was the video, guys. It wasn't much of heap exploitation. It was actually more of understanding how the heap and how the stack works, how some allocations happen, what happens after you free, what happens when you create a global variable, when you create a fixed size buffer like this, and allocate memory with malloc, dynamically allocate memory, and stuff like that. And I hope you learned something from the video. If you find it helpful, leave a like and subscribe to the channel to support me. And have fun. See you in the next video. Bye.